At this point, we've seen what a differential equation is, and we've also gone through some examples of verifying that a function is a solution to a differential equation, and also seeing how to come up with the solution to a differential equation. What I'd like to talk about here is ways to approximate the solution to a differential equation. So to start that off, let's first recall the notion of a linear approximation. This is also what we call a tangent line or the first degree Taylor polynomial approximation. And in particular, we want to talk about approximating near the point, say, x equals a. And the idea of using this to approximate is for b near the value x equals a, we would be able to say that f of b is now approximately equal to f of a plus f prime of a times b minus a. So we would be able to use this to predict values or approximate values for the function f. It turns out that the technique of Euler's method is going to be one in which we can use the notion of a linear approximation and repetition in order to find or approximate points on the solution function to our differential equation. So to start to focus on that, let's consider an initial value problem. And let's call it dy dx equals g of x comma y. And our initial condition will be the data point y of x sub 0 equals y sub 0. So we're identifying that the solution to this differential equation passes through the point x naught, y naught. So the goal here is to use this information to hopefully approximate the solution function evaluated at a different point. So let's approximate y of b. So again, y being the solution of this differential equation. So the way we're going to approach this is the following. One, we're going to split the x interval. So the interval from the initial x value up to the one at which we'd like to approximate the function. Let's split this up into n subintervals of equal width. We'll call that width delta x. And we're going to then define the edges of these subintervals in the following way. We're going to let x sub k represent x sub 0 plus k times delta x. So this notation is hopefully familiar. This is exactly the same way that we approached Riemann sums. Delta x being the width of each of our equal subintervals, and using xk to mark off the edges of those subintervals. Then, once I've established that, then the idea is that we can use a linear approximation. So if I now want to approximate y of x1, then think of x1 here as the kind of the value we want to approximate our solution function at. And I'm going to use a linear approximation. So according to our formula above, I would need to take my known y value. So that was y of x sub 0. The derivative at that point times the change in x here. So to be clear, we're using our linear approximation formula, and we're treating x sub 0 as the a value. It's like the center. And we're hoping to find or approximate the value of the function nearby. Nearby here is x1. And we're going to use that to find that next value approximately. Now, for a few things, I can write this in shorthand a little bit better. So following the convention that we have up here we said we're going to let y of x sub 0 be called y sub 0. Same thing here, y of x1, let's just call that y1. And then we're saying that that is approximately equal to y0, the derivative of y at x0, which, again, looking at our given differential equation, I can call g of x naught, y naught. And we're multiplying that by x1 minus x naught. That's the width of our subinterval. That's delta x. So that's just a shorthand way to write what we have on the line above. So then you can think about what comes next. Once we estimate y1, then what we can say is we can use that to roughly estimate y2. So y of x2, which we're going to call y2, is approximately equal to y1 plus the derivative of y at x1, which we can call g of x1, y1, times delta x. And then next we can try to approximate the value of the function at x3. So I'm essentially jumping along the x-axis by these step sizes of delta x. And we are now going to be able to use a bunch of linear approximations until finally we get to the desired x value, which we're using here to call b. But in general, what I'd like to formalize is this equation. So we're saying that if I want to approximate the value of the solution function at xn, then I can do that by taking my approximation at xn minus 1, adding then the derivative of the solution at that previous point times delta x. And so this is going to be our general process, and this is going to be our general equation that we want to keep in mind here. Now, in the next video, I'm going to go through a concrete example to see what the pieces of this equation look like. But to be clear about this process, what we're saying is, in terms of what this would look like, of course, the key thing here is that with this differential equation, we don't know what the solution function is. Consequently, we don't really have a graph of the solution function. So this is making some assumptions we don't have. But suppose that my solution function that's for this differential equation is this graph. So if that's the actual solution here, what we're saying is suppose I have the point that it passes through that's given in that initial condition, x naught, y naught, and the other information we have is the derivative of the solution function at the point x naught, y naught. So we have complete information then about the slope of the line tangent to this function here. So let's think about what that would look like. That would look something like this. And that means if I wanted to follow along that tangent line to, let's say, x1, then the estimate of the solution function there would actually be this point on my pink line. So this would be our estimate of y1. Of course, the true value is a little bit above that. Then you could think about what we can also use the differential equation for is to find the slope of the line tangent to this curve at x1. But one thing that we're going to have to account for here is I'm not actually going to use the line exactly tangent to that because we're going to have it pass through this point instead of the actual point because this is all a prediction. So this kind of error that we had here is kind of compounded throughout this. So I would then follow this slope and use that to say predict what the value of the function would be at x2. And I would predict this here. And we could continue this process as far as we needed to get to the desired endpoint where we're hoping to approximate the solution. And notice that along the way we get several other data points. So in some sense you could construct an approximation of the graph of the solution as well by trying to connect all of the data points we get along the way.